So welcome to the Picture Language Seminar. We have a couple of interesting talks coming up in the next 2 weeks. Yasu Kawashigashi will talk next week, Xiaogan Wen the week afterwards. And today we're really happy to have Quanhua Xu. He's talking to us from France, the University of Franche-Comté, but he also is connected with the Harbin Institute of Technology, where he founded the Institute for the Advanced Study in Mathematics. And Professor Xu is well known for his work in non-commutative geometry, especially analytic work, and will talk to us today about Mikhlin type Fourier multipliers on free groups and free products of Neumann algebras. So it's yours. The floor is yours.
Okay. That's fine?
Yes.
Okay. Okay. So we first to thank author for his kind invitation to this wonderful seminar. I just noticed that the seminar is well organized with many, in fact, interesting talks. The talk I'm going to present today is based on a joint work on progress with Tao Mei and Eric Rigar. So the title is The Fourier Multiplier on Free Groups and Free Product of Neumann algebra. So this concerns the non-commutative analysis. So mainly on free groups. So I start my talk. I don't know you, do you, so maybe this part, do you see the whole screen or?
Yes.
Or this? Okay, okay. So I start with some very basic definition. So in this talk, gamma will denote always a discrete group. Is left regular representation. Lambda is defined in the following way. So for any element G in the group gamma, so lambda of G is the unitary operator on A2 of gamma, which maps data H to data GH. So you can see from this definition, lambda of G is just the left translation on little A2 of gamma. Then the group von Neumann algebra is denoted by this notation. So this is in quantum group. This is a quantum group notation. Is just the bicommutant of lambda of gamma. So all lambda of G for G in gamma in B of A2. So B of A2 is the algebra of all bounded linear operators on A2 of gamma. Okay. So another way to define this von Neumann algebra is just by taking the Weierstrass closure of all polynomials in indexed by gamma. Here the sum are all finite sums. So this is just think of the trigonometric polynomials. So this is the non-commutative analog of the trigonometric polynomials in the usual case. So here all the sums are finite. So C of gamma is the group algebra of gamma. Okay. So this is a evolution algebra. Also, this gamma hat is equipped with a normal faithful tracial state. So defined by this vector delta E is the identity of the group. Okay. So this is a vector state which is tracial and faithful. So in this talk, I'm going to consider the Fourier multiplier on AP space. So in this case, because our von Neumann algebra is non-commutative, so the AP space, the usual AP space, have to be replaced by the non-commutative AP space. So gamma, so here AP of gamma hat is the just by definition the combination of gamma hat. So gamma hat is A infinity. You see, gamma hat is A infinity with respect to the norm defined by the trace. Okay, so for any x in gamma hat, we take the absolute value, then we take the power p, then we take the trace. The trace is just the non-commutative integral, then all to power 1 of p. So this is the norm on gamma hat. Then we take the completion of this norm space, we get a Banach space. So this Banach space is our AP space based on gamma hat. Okay, so this is a non-commutative AP space. Okay, then we define the second definition is the central notion of this talk, the Fourier multiplier. Okay, then we are given a function defined on gamma, a complex valued function on gamma. Then we define the multiplier on polynomials, first on polynomials. So this map M phi sends any polynomial to another polynomial just by multiplying each coefficient by phi of g. Okay, you see just the difference between the first polynomial and the second one, the image is just here. We just add multiply each coefficient by phi of g. Okay. So this is a linear map. If this linear map extends to a bounded map on AP, then M phi is called an AP multiplier. Okay. So this is the extension of the usual definition in the classical case. Okay. And similarly, we define CB, here CB is completely bounded. So if the map N phi is completely bounded, then the multiplier is called a CB AP multiplier. So this notion completely bounded, for those who have not are not very familiar with this definition, here is just, you can take this as a definition. So this map N phi on AP is said to be completely bounded if the following map, and this is the tensor map, is this tensor map, okay, is bounded. So this is the usual, this is now this boundedness is the usual boundedness of a linear map. We have the B of A2, of course, this is the infinity matrix on A2. So here we have a bigger von Neumann algebra. So we have a big AP space. In fact, the non-commutative AP space based on B of A2 is just the usual shortened P class, SP. So you see here, SP is for the usual shortened P class, SP. If this tensor map is bounded, then M phi is called completely bounded. And its CB norm is just the norm of this linear map. Okay. In this talk, I will consider only CB multipliers. Okay. So the corresponding space is denoted by MCB of AP, MCB of AP. So this is the definition. So our aim is to find criterion on phi so that phi is a CB AP multiplier. Okay. So this is our main task. But this task is very hard. Usually, it is impossible to characterize the AP multiplier for finite p. So in the next 2 slides, I will give you some no result. In fact, there are not very many results in the non-commutative case. Okay. So before that, here just some very basic definition, very basic property of Fourier multipliers. So the one case is trivial. The case P equal to 2. So you see, if P equal to 2, we have a Hilbert space. So A2 space is a Hilbert space. In a Hilbert space, then we have this A2 Fourier multiplier coincide exactly with bounded sequence on gamma. So this is bounded function on gamma. And we have also a very nice duality. So phi is a CBAP multiplier if only if it is a CBAP prime multiplier. So this duality allows us to consider only 1/2 of the interval. Okay, for example, we need only to consider P between 2 and infinity. And the last one is also very elementary. So if 2 indices, P and Q, P less than Q, then the Q multiplier are necessarily the AP multiplier. Okay. So these are just a very elementary property. Okay. So now I give you some null result. In fact, most null criteria are concerns the commutative case. So the group gamma now is abelian. Okay, gamma is abelian group, then gamma hat is exactly the dual group of gamma. So gamma hat is a compact group in this case. Okay, and AP is just the usual AP on this compact space. On this compact space, in this case, we have the characterization of a infinity Fourier multiplier only for P equal to infinity. Okay, so the infinity Fourier multiplier are exactly the Fourier transform. Here mu hat is the Fourier transform of mu for mu bounded measure on gamma. Okay, so in this case, the space of CB a infinity Fourier multiplier coincides with the Fourier transform of bounded measures on gamma, on dual group gamma. And also, in this case, bounded a infinity multiplier are automatically CB, But in general, for P finite, you see, for finite P, we don't have any nice criterion for AP multipliers. So we don't have any, it is impossible to find any characterization in this way for finite AP multiplier. Okay, so this is the abelian case in general. In the abelian case, in a very special case, the Euclidean space. Okay, so here I consider discrete case only. Okay, the discrete case, now the group is Z to power D, the integer group to power D. Okay, this Z is the integer group. Then the dual group is the D torus. Okay, the dual group is D torus. You can also replace the discrete case by the Euclidean space. So you can replace Z by R, then R to power D. The dual group is itself. Okay. Here I consider only the discrete case. Then phi, function phi on Z to power D is said to satisfy the usual Mikhlin harmonic condition if the following condition star is verified. Okay, so we have some constant C such that for any multi-indices in Z to power D, okay, and also for any multi-indices alpha is the derivation. Okay, we have this partial to power alpha is the partial derivation. If all these quantities are majorized by a constant C. Then in this case, so phi is called a Mikhlin-Haumont multiplier. Okay. So the conclusion of this theorem, this is a very fundamental theorem in harmonic analysis, is the conclusion says for such multiplier are a p multiplier for any finite p. So when I say finite p, that means p is strictly between 1 and infinity because we have the duality. So p equal to 1 corresponding to p equal to infinity. So if p strictly between 1 and infinity, so in this case we have a p multiplier. Okay. And also because we want to have the CB version. The CB version, so this theory, this is the collective theory proved by Mikhlin and Haumont. So first by Mikhlin with some stronger condition than by Haumont in the 60s. In the 60s, so then this theorem was extended to the CB case. In fact, for non-commutative AP space, by Burgan in one dimensional case. In fact, the final version I stated here is due to Zimmermann, who proved that if we strengthen this condition star for all alpha in the set 0, 1 to power d, that means if all coordinates of the multi-index alpha are either 0 or 1, then we have this inequality. So in this case, so phi is CB. That means we can consider the tensor with the shortened P class. Okay, with the shortened P class. So this this is in fact the essentially the unique fundamental theorem in the classical case for this very classical case. Okay. So before going to the non-commutative setting, I give you two very important examples. First one is the Ricci transform, and this is defined by this formula. So we still in the integer group case. So this is for any j between 1 and d, we define this function phi j. So this is nj over the norm of n. Okay. So this multiplier is a Mikhlin-Haumont multiplier, and also the associated multiplier is CB. In this case, is CB, and in case d equal to 1, in the one-dimensional case, we get the Hilbert transform. So this is the first example. The second one is the so-called Littlewood-Paley decomposition. So we decompose the integer group z to power d in disjoint, essentially in disjoint annulus. You see, this is delta k is just the annulus or radius. In fact, radius 2 to power k, another 2 to power k plus 1. Okay, then we introduce a multiplier function phi defined by this formula, this infinity sum. Okay, with coefficients epsilon k equal to plus or minus 1. Then this is again a CB. So gives us a CB AP Fourier multiplier. So why the title is called the Littlewood-Paley decomposition? Because you will combine this result with the classical kinship inequality, we get the decomposition, the famous Littlewood-Paley decomposition for AP space, for P strictly between 1 and infinity. So these are two fundamental examples from harmonic analysis. Okay. Now I shift to the non-commutative case. So this a typical example is the free group. So in the free group, we have some very interesting result. So here just is the definition of the free group. We need is natural length. Okay, so we take a free group on infinity generators GK, and every edge in the free group different from the identity can be written in this reduced form. Okay, this is reduced form with letters so GI1, etc. So here it is important that I1, the first index is different from the second one, and second is from the third one, etc. Okay. Then in this reduced form is very important. We will use very often element H in this reduced form. Okay. Then the length of H is defined by this formula. It's just the absolute value of all powers in the letters. Okay, so we call this one as for example GR1 as the first letter of H, the first letter of H. Okay, so in this case we have this important result about the radial multiplier, the A infinity. So here we consider A infinity case. So you see, so this is a F infinity hat. So this is A infinity case. So this phi now is a radial function. Radial function means phi of H depends only on the length of H. We are on the length of H. So this is a radial function. So in this case, we have a characterization of CB A infinity Fourier multiplier. So this so phi is a CB A infinity Fourier multiplier if and only if this is infinity matrix. So this is the infinity matrix, and moreover, this is a Hankin matrix. You see the is entrance depend only on the sign I plus J. So this is the infinity Hankin matrix if and only if this infinity Hankin matrix is a trace class operator. So this is a trace class operator. Okay. This result was extended later by Ozawa to more general hyperponic group or hyperponic graph. Okay. So this is a infinite case. In fact, there is a very interesting problem, big problem. So how to find some nice criterion for radial Fourier multiplier for AP for finite P, but the problem is still open. So in this talk, I give you some results in this case, but they are not radial Fourier multiplier. Okay. A more recent result just published 3 years ago by Tao Mei, my collaborator Tao Mei and Higar. They prove some free analog of the usual Hilbert transform. Okay. Of the usual Hilbert transform. So here we are given a sequence of signs epsilon k plus or minus k is a sequence of sign. Then we define the corresponding multiplier. So you see in this way. So H now is again in this reduced form. H is in this reduced form. Then we define H epsilon of A lambda H on this reduced form just by multiplying lambda of H by a sign by plus or minus 1. And this plus or minus 1 depends only on the first. You see, only on the first. This is the first, not the first letter, the first block. You see, only on the first block of the reduced form. So you see, so we have the I1, the index I1 here. Also, we have the sign of K1. So K1 is a general integer, can be negative. Okay, if K1 is negative, we add, you see, our sequence is a double sequence for K positive and also for K negative is a double sequence. So we just multiply lambda of H by plus or minus 1. So we get a map. This is a linear map. Then May and Hegard proved that this linear map H epsilon is CB on a P for any finite P. Okay, for any finite P. So this is a very significant result. Okay. So this are the first part of my talk, in some sense, the introduction about the setting of our work and also some null results. Now I'm going to in fact, in some sense, to extend this Hilbert transform to more general multiplier. So this is the contents of the lecture tonight. So the title is free multiplier on the first letters. Now the first letter can be the first D letters. So we are given a integer D, a positive integer D, then we can define the action of the D torus on our group algebra C of H infinity, F infinity in the following way. So you see that this again is a multiplier. Okay, so H in this reduced form. Okay. Then we define so for any Z in the D torus, we define so Z1, K1, etc. onto ZD, KD. Okay. Here we can, for example, this one can be put as I1. You can put this I1 is the same. Also, this can be the D1. That means now the multiplier depends only on the first D letters or D blocks. You can see this on the D blocks of the reduced form. And also the plus or minus 1 in the previous Hilbert transform, plus or minus 1 now are replaced by this complex number of modulus 1. Okay. So our first result claims that this map, this new map pi D extends to a CB action of the D torus on LP, on our non-commutative LP space for any finite P, So in fact, what we wish to prove at the beginning is the corollary of this theorem. From this theorem and the usual transference principle in harmonic analysis, there is a very useful and powerful principle called the transference principle. Then we can get this corollary. So this is a Fourier multiplier theorem. Okay, so we assume so phi a function on z to power d satisfies the following condition. So this you see you can recognize this condition. That means the phi is a Mikhlin horizontal multiplier in the d-dimensional case. You see in the d-dimensional case, then we define another multiplier on the phi group. So the new multiplier is on the phi group. You see this new multiplier only is defined according to the first D block of any H in the reduced form. You see this, we have K1 and until KD. So here we have the H is again in this reduced form. So the multiplier depends only on the first D block of the each reduced word. So this new map is again CB on AP for any finite P, Yeah. So this is, in fact, is our very first objective to prove such a multiplier theorem. So change from this result, of course, extends the previous Hilbert transform. In fact, we here the phi group is just the infinity phi power of the integer group. So this result can be extended to the free product of general groups. Okay, so this is the end of the present slide. Okay, so here we replace the integer group by any group gamma, Okay. Then we take and we consider the infinity free power of gamma, so denoted by gamma infinity. So you see in the free group case, we have gamma is the integer group Z. Okay, now we have a new group, gamma infinity. And before we define an action, now the action, this is gamma to power D. This is the direct product of gamma. Okay, we have two group algebras. Okay, so this, you see pi D is defined in the same way. In the same way, if H is written in a reduced form, if we have a word, a reduced word in the infinity free power of gamma, then we write it in a reduced form, then our new map pi D is defined by this way, depending only on the first D letters in the reduced form. Okay. So you can imagine the statement is again, this new map is CB. Okay, this new map is CB for any finite P. Okay, so from of course, from now we have two different AP space. First one is AP gamma infinity hat, and second one is tensor. So gamma D hat tensor gamma infinity hat. Again, the corollary is a Fourier multiplier theorem. Okay, a consequence application. So we get now if gamma is, so now we need an additional assumption on gamma. So gamma is hyperlinear. Then if we have a CB multiplier of AP gamma D hat. Okay, so you can imagine this is just if gamma is the integer group, so the gamma D is the D torus. In this case, is D torus. So we have a CB multiplier on the D torus, then we can transfer this one to a Fourier multiplier on the free group. Okay, in the case of free group. So this you see we define again in the same way a new map on gamma on gamma infinity. So depending only on the first D letters, So this new map is CB on gamma. Okay. This essentially the same statement. Essentially the same statement. Here why we need this additional assumption that gamma B.
Could you explain, excuse me, could you explain what hyperlinear means?
Hyperlinear, that means gamma can be embedded in some sense, approximately in the ultra product of a unit group, matrix unit group. Okay. So this is equivalent to another property. So the group of von Neumann algebra is Q-wave. Q-wave means is the quotient of a weak algebra. Here weak, WEP, means weak expectation property. So the hyperlinearity is equivalent to this, but the definition of a hyperlinear group, gamma is a hyperlinear group, is gamma can be embedded as a subgroup of an ultra product of unitary group on for example, on needle A2. Okay. You can take also the matrix, the unitary group of some finite matrix. Okay, finite matrix. So this is related to Kahn's embedding conjecture. It is whether any von Neumann algebra can be embedded in the ultra product of a hyperfinite 2-1 factor. This is essentially the same. Okay. So this is for example, the Kahn's embedding conjecture for group is so ask whether any group is hyperlinear. Okay. For example, any group is harmonic. Okay, this is the group case, the free product group case. In fact, we can prove as the title of my talk, in the case, we have some more general result for the free product of von Neumann algebra. Okay, in fact, it is easy to prove all these results in the two previous slides. Also, for example, in the previous slides for the group case, in this more general setting, okay, in the general setting of von Neumann algebra. Okay, so here I just recall to you the definition of the contraction of free product of von Neumann algebra. Okay, so pardon. So we are given a family of von Neumann algebra, AK phi k. So the phi k are faithful normal states. Phi are faithful normal states. And as usual, we denote by AK circle. This is all elements of AK with vanishing moments, with vanishing expectation. Then we form this W. So W is, you see, W, the formula is quite complicated. You just imagine, so you will have the constant term. This is vacuum, the vacuum term. This is a one-dimensional space generated by the vacuum state. Then we have all these polynomials in some sense, okay? All these homogeneous polynomials. You see this Wn. You can see that the nth part. So this is just the space of all homogeneous polynomials of degree n, Then we put all this together, so we get a evolutive algebra. So this algebra W is called the algebraic free product of the AKs. So this W is just the algebraic free product of the AKs. Okay. Then also in this case, the states phi k determine a unique state phi on W, so such that the restriction of phi to AK coincides with phi k. Okay. So from the phi k, we can define a unique state on this algebraic free product. Okay. Then the von Neumann free product of the AKs is just the von Neumann algebra represented by the GNS contraction from this evolutive algebra equipped with the state phi. Okay, so you see the contraction is quite easy. In this case, we have a von Neumann algebra equipped with a normal faithful state. Okay. So as I said before, this part, the nth part, Wn, is the space of homogeneous polynomials of degree n. So we have a natural projection on the A2 level. Then here we have A2 space, also AP space. On A2 level, all this Wn are orthogonal. We have a natural projection. So this projection is Pn. So Pn is a projection onto the homogeneous polynomials of degree n. Okay. Also, we will need P, and at least n is just identity minus all the previous one. Okay. All the previous one. So this is the contraction of free product of von Neumann algebra. Okay. The contraction now is very standard. Now we can formulate our central result in this talk. This result so improved all the previous case, all the previous result in the group case. So our general assumption is the following. So it is remarkable to here we fix one p. You see in all the previous result p vary between 1 and infinity. here we fix a p, index p between 2 and infinity. And we take a map Tk on AK, on the volume algebra AK, which is unital, state preserving, and extends to a CB map on two spaces, on two AP spaces, the trivial one A2. I just say A2 is a Hilbert space. So in fact, A2 case is usually the trivial case. And another non-trivial case assumption is on AP. So in AP case, so this map TK is bounded on A2 as well as on AP, such that the supremum of all the norms, CB norm of TK, is finite for Q equal to 2 and P. So this is the general assumption. This is a general assumption. You can imagine there are many such maps because we want to consider free product. So here this is on each level AK we have such a map. Okay, then we want to define in some sense a new map from this family of maps AK TK. So this new map is TD. Okay, you see using our construction of free product of monomial algebra, we consider a monomial. In this case, you see this is a monomial. Yeah, also a reduced word. You see a reduced word in this case. Then we define this T to power D in the same philosophy before. So this new map, you see, is defined. We just change the this letter. So this is this letter in the reduced form of X by DID of AD. We don't change all the other factors, all the other letters. We only change this letter. Okay. So this letter in this case is we put the DID. So this is TK. Okay. TID here. So this is a new map on free product, the new map on free product. So our the central theorem, the central result of the talk is so claims that such a new map is CB on a P space of the free product. Okay, on a P space of the free product. You see that on a P space of the free product. And we can compute the CB norm of this new map. The CB norm is majorized by the two constants here. We have the C2 and the CP. And also, of course, we up to some constant depending on P. So this is the central theorem of the talk, central result of the talk. So you can see in this conclusion, in this final inequality, we only use these two constants, C2 and CP. Okay. That means we only use the action of TK, of each TK on A2 and AP. Here is the assumption is on A infinity, okay, A infinity. Okay. But we don't need the AK. So this is the sense, the meaning of this remark. We need only to assume that the map TK maps AK into AP. Okay, so for this fixed P, so this is the strength of this result. Very important in application. Okay, so in fact, this central result implies quite easily the result in the free group case, also the result for the free product of groups, free product groups. So this is a general theorem. I don't know how many. I should take to watch out my time. How many time?
About 15 minutes.
Okay. I still have 10. Very good. Okay. Okay. In the remainder of 10 minutes, I try to explain, to give you some very vague idea of proofs, and also in fact the final result in my talk is also interesting for its own right. Okay. Now I'm trying to prove this, to give you some vague idea of the proof of this central theorem. But in fact, if we need only to consider, in fact, the essential part is the case d equal to 1, and also all the tk are star homomorphism. The general case can follow quite easily from, can be proved by using this special case. So this is the first ingredient of proof. Okay, first ingredient of proof, a Cotlar type of formula. For those who are very familiar with harmonic analysis or the Hilbert transform, we know there are many different proofs that the Hilbert transform in the classical case is a bounded operator on AP. One of very elegant proofs is due to Cotlar. In fact, Cotlar found a very beautiful formula for the classical Hilbert transform on the unity circle that allowed us to use some iteration. So in this case, we follow the Cotlar argument. Okay. So as I said, just to say, we consider the case d equal to 1, our T1 depends only on the first letter. Okay. And all the tk are star homomorphism. All the tk are star homomorphism. So we have this t, now we denote the t1 by t, and also we will need another one. This is happening very often in the free case. So our operator is defined, all our maps are defined according to the first letter. By symmetry, we can also consider another family of operators according to the last letter of the reduced word. You see, we have the first letter and also we have the last letter. You see, the last letter is just op. Here is op for opposite. So T op is opposite. So we have the same map defined in the same way, depending on the last letter of the reduced word. So this is T op. Okay, T op. Then we also need, so this part is quite technical. So you can skip. You can skip this part. We need some parallel products on the algebraic free product W times W. Okay. Only consider the first one. Okay, the first one, x dark 0, 1, y. Here, h epsilon is something is a Hilbert transform. The free Hilbert transform we used it before. So now epsilon, the sequence epsilon equal to epsilon k is a sequence of symmetric, independent random signs, the plus or minus 1. Now the random variables. Then we take expectation on epsilon on all this epsilon k, so we get a new one. So this definition looks complicated, but it is very easy to understand. So this, you will consider the product of two words, elementary tensors. For example, xy, both xy are elementary tensors, so two words. Then we consider the product. The product is in general no longer reduced in the reduced form. Okay, with the construction of the free product, this product is not in general in a reduced form. So this product is decomposed as a sum, a finite sum of reduced words. So this parallel product just connects all reduced words in this decomposition that don't start with the same algebra as x. So this one, you can skip this part, okay? So this is the Cotlar type of formula, okay? The first one is quite easy. You will take any xy in this algebraic free product. Then we consider the product of the two images, T of X, T of Y, okay? So in fact, we want to write this product as something like this. You see on the right. So the first term is T outside. Then inside we have X without T and T op applied to Y. And for the two others, we have the same character. Okay? But in general, this formula is not true if we don't take the projection on the letter at least 2. So up to this projection, then we have this. This is the usual. In fact, we have the usual Cotlar formula. Okay. Here, the first equality is quite easy. Okay, quite easy. So what is communicated is the second one. For the second one, in fact, for the remaining, this is the small part of homogeneous polynomial of degree 1. So you can see this, just the polynomial of degree 1, the remaining part. For this part, we need this parallel products. Okay, then we have a similar formula. We have a similar formula. So I go very quickly for you in the next slide to show you how Cotlar argument works in this form. Okay, I show you all the steps. We have 4 steps. We have 4 steps together. So we wanted to estimate for any x in W. We want to estimate the epsilon of T of x, the epsilon of T of x, or a 2 epsilon. You see the a2 epsilon of T of x. Then we write this as T of x times T of x star r. Okay. So this is the product. You see this product, we wanted to use the previous Cotlar type formula. Okay. So now y is x star. You see y is x star. Okay, y is x star. Then this product is decomposed as a sum of 3 parts. So the first one is constant part. So this is constant. We take the mean of the product. The second one is a part of homogeneous polynomial of degree 1. Okay, and the last one, the remaining part. So for this, so the first part is easy to deal with. Okay, so what is important is what is difficult is first, second, and the third one. Okay, and for this 2 part we use the previous Cotlar type formula, and the idea is to prove if T is bounded on AP, then it is bounded on A2P. So use this, you see this decomposition. So you have, if T is in X, T of X in A2P, then this, the product, you see the product inside is in AP. Okay. Then from this, so this is the main step. With this main step, so I said before, the case P equal to 2 is trivial. So Fn is trivial in the Hilbert space case. Then we use an iteration argument to show that if T is bounded on AP, or the T is bounded on AP for all powers of 2. So if P is the power of 2, then everything is okay. Okay. So the main step is step 2. The step 3 immediately follows from step 2. The last one is also easy. This is a classical one. Then for any P between 2 powers of 2, we use complex interpolation. Then then we conclude the proof. Okay. So this I may use, but just last a couple of minutes to show you the last slide. This is the last slide of my talk. Okay, I give you the whole page. Okay, this is the second ingredient of proof. In fact, the formula I said it before. So this the main part of this part is this length reduction formula. So you again we use the free product contraction. We take any polynomial, okay, any polynomial x in WC, just this is polynomial. So this polynomial is decomposed again as three parts. Okay, the constant part, and also the second one. This is the part of homogeneous of degree 1. First one, homogeneous of degree 1, and also the remaining part. And also here in more details, the remaining part is a finite sum. Here is a finite sum of tensors. You see tensors of form AI tensor BI. Okay, AI tensor BI. And AI is in the algebraic AI circle. And BI is in W circle. So with vanishing mean. So each BI is of vanishing mean and does not start with the same letter from AI. Okay. So this just come just from the contraction of free product. Then we have this length formula. Okay. So the epsilon of X is decomposed according to these three parts. The first two parts are quite easy. Okay, this is in fact to estimate the norm of the second part. We need a inequality in the p equal to infinity case due to Vn down Vn y equals. Okay, for this third part we have two. The third part gives us two different norms. So one is current norm. This is so W1C. This is the usual the current norm, and the second one is the real norm, current and real. Okay, so this language is taken from operator space theory. For those people who are not very familiar with operator space theory, you can just understand this as some norm easier or better to the period to the period epsilon. Okay, this is in fact we reduce this is length reduction. We reduce the length of this one to another degree, less degrees. Okay, so this result in fact allow us to reduce the central theorem for any D and for any maps TK to the special case where D equal to 1 and all TKs are star homomorphism. Okay. So this, of course, this reduction formula is also interesting for its own right. In fact, it extends a previous result proved by Mark Young, Harvey Baxter, and myself 10 years ago. Okay, more than 10 years ago. Okay, that's all of my talk. Thank you very much for your attention.
Thank you very much for an absolutely beautiful talk. You explained things so nicely that now we can hope to look at the proof and be able to go through it.
Thank you.
There are many questions.
Thank you. Just open.
Are there no comments or questions?
Sorry, just one question. So in the Cotlar typewriter formula that you mentioned, you had that projection 1. So what's the precise definition of that P1?
P1 is in the so this is the projection on the space of homogeneous polynomial of degree 1. Okay.
Ah.
It is.
And the P greater than or equal to 2 is the rest part.
Yes, the rest.
Yeah, so the Cotlar formula is only satisfied for the part greater than or equal to 2, right? For
Yes,
P1.
yes. This I said is, for example, in this case, the formula is quite easy. This is quite easy to prove. So what is communicated is the second part. So the second part we need some different products. Okay, this one. Yes, you are right.
In your talk, you mentioned that theorem 5 is very useful in applications. Could you tell a little about the applications?
Okay. In fact, my main concern, in fact, our main concern is to prove some kind of result of this kind. For example, for the video case, the video multiplier. Of course, then we prove because we couldn't prove this, then we find some result around. So one possible application is to, for example, because you to the characterization in I mentioned before the rigid transform or hybrid transform. There are some very interesting application of the commutator with the rigid transform by the so-called BMO or the shortened SP class membership. Here, it is possible in some sense. One important for me, one interesting question for me is to find some free analog of such result. So how to we have, for example, here we have the free hybrid transform. We can also consider the free hybrid transform, some kind of commutator analogous to the classical case, So do we have a kind of BMO characterization? Or in the AP case for P finite, for the shortened P class, do we have a shortened P class membership? Okay. Such a result could have and might have potential application to non-commutative geometry. For example, in some recent result proved by Fidel, Sugojev, McDonald, and Xiao, they prove some commutator in the quantum torus case, some kind of the commutator with the quantum torus rigid transform gives some Dixon matrix formula. Okay, this in fact the membership there is the shortened some weak shortened P class or shortened SP1 class. Okay, so this is also explained in Alan Kahn's books on non-commutative geometry. So there are some potential applications. But from my point of view, is on non-commutative analysis. In fact, another potential application is on the AP is the approximation of AP space or the convergence of Fourier non-commutative Fourier series. Here we consider Fourier multiplier. The usual, for example, the very classical Fourier multiplier in the classical case, we can take the Poisson kernel or the Fourier kernel or just the Dirichlet kernel. Then we can consider the corresponding convergence of the Fourier series, potential or pointwise convergence. Here a further study would be on the convergence of Fourier series with some different summation methods. Okay.
So, Kuznets, did you have a question about transference?
Which transference?
Hello, my name is Yulia Kuznetsova. I just wanted to ask for one of your tools. You use a transference principle. So where does it? By whom is it? Where does it come from?
And
Because I know
this
something made by Habish,
maybe
but apparently it's
maybe this
another
is,
one.
I'm not sure if this is the transference principle you have in mind is the same as this one. Okay, before. In fact, this one, this is the transference principle from harmonic analysis.
Yes. Uh-huh.
developed by Koifman, Rockman, and Weiss. But all of them are people, in fact, American people from harmonic analysis, a very important harmonic analysis. So I repeat. So this Koifman, I think Robert Koifman, Rockberg, and Weiss.
Koifman.
Yes, Koifman. I think Koifman from now I think in Cotlar, and Rockberg and Weiss, both from St. Louis, Okay. So in the
It's
80s,
very old, in fact.
yes, in the late 80s, they developed a transference, a general transference principle. In fact, at the very beginning of this principle, so goes back to Albert Carleton, another harmonic analysis, Carleton, who published a short paper in PNAS in the 60s. Another paper who developed a transference principle to prove a very important algebraic theorem for groups. You see, in the 60s, so Carleton already used this transference principle to deal with an analytical problem on general groups, not abelian general groups. But his concern was on the algebraic theorem. Then in the I think in the 60s or in the 70s or 80s, so Koifman and Rockberg and Weiss developed this transference in more general setting. They have a short book, this regional conference, this American Mathematical Society regional conference series. In this short little book, they developed the theory in the general setting. Okay, so this is the transference. So we can transfer. For example, here we transfer the general setting to the integer group case. But in the integer group case, we have many different tools, okay, analytical tools. You see, they here in the group. Well, so what is here the difficulties? The most important difficulty is on the field group. We don't have much available tools, and we don't have much available techniques. So usually we have to go back to the classical case. So here the transference principle allows us to go from the field group to the classical integer group case. So this is the power. This is the power of this transference principle.
So do you have a new paper about this work?
Not yet. This is a paper just we started. Still on progress. Still on progress. We proved this. In fact, we proved this. This set of results just I think this is why I didn't send you my the title of my talk before. No,
when did you prove it?
Maybe very soon. So, very new, we are very fresh result.
So when will we hope to see the paper?
Maybe by the end of the year, or at least at the beginning of next year. I'm sorry.
Are there any more comments or questions?
I have a question. This is Robert Lin. It's not directly pertaining to the main results, but just when you talk about classifying completely bounded Fourier multipliers, is there some result for completely positive Fourier multipliers?
Yes, completely positive, but for Fourier multiplier, there are some, but usually for completely positive it is easier in some sense. For example, in the group, I didn't mention another very fundamental theorem of Hegel in this part. So in fact, the analysis on field groups, harmonic analysis on field groups, start with a pioneer work of Hegel in the 70s. And that work who proved the reduced C-star algebra of the field group has the Gordon-Diggs approximation property. That means the matrix approximation property don't solve a non-standing open problem in C-star algebra. So in that paper, Hegel proved, in fact, this length function, the natural length function on the field group, is negative definite. Is negative definite function. That means when we take the Fourier multiplier, the power, you see now you phi, the function phi is e to power minus d. If this function psi is e to power minus dk, tk, t for t positive, tk, then this function is completely positive in AP for all p. Of course, in this case, is extended to also to CB multiplier on AP space. Okay, this is the very first result on harmonic analysis on the field group. So due to Hegel, very important. So this, in fact, this Hegel work opened the avenue, the big avenue of harmonic analysis on field groups and also on many other properties on group geometry properties. For example, then in this paper, Hegel introduced a property for the reduced C-star algebra. This property has then developed into, now today is called Hegel property, a very important property in the theory of geometry group theory, of the geometry group theory. So you are right, there are some for completely positive, the result are in some sense is easier. Then usually for completely positive, we can go back to the A infinity case. Usually we can go back to the A infinity case. So here for the usual AP case, the order, in fact, most of the AP multiplier for finite P cannot be completely positive. Okay.
Thank you very much.
You're welcome.
So in mathematical physics, another type of positivity, reflection positivity, often comes up. I wonder if that comes into some way into this analysis.
Yes, as I mentioned here, your positivity is the same as complete positivity or complete positivity.
It's a slightly different condition, which involves the opposite algebra. So we could talk about it privately.
I don't know, I don't know. to be sure, not that.
Well, if there are no other comments or questions, I'd like to thank you again for an absolutely wonderful talk, very inspiring talk, and we look forward to your papers. Bye-bye. Bye-bye.
Thank you very much.
See
Thank
you
you.
next week.
Thank
See you
you.
next week.
Bye-bye. Thank you to all of them, all of you for listening to the talk. Okay. Bye-bye.